Yes, we can begin. So, welcome everybody to the second talk of the day. We have Nidhi Sudhir from University Wisconsin-Madison, and she's going to talk about topological contribution to Bogoliubov coefficient for cosmological gravitation particle production. I'll
Thank
maybe
you,
send you
Anish.
a reminder when 5 minutes are left.
Yep, that would be great. Thank you so much. So firstly, I want to thank the organizers for inviting me to this seminar series. As Anish mentioned, I am Nidhi. I'm a final year grad student at the University of Wisconsin-Madison, working with Daniel Chung. And today I want to tell you something about cosmological particle production. What exactly? I want to introduce a concept, a mathematical concept called Stokes phenomenon, which will allow us, sorry for that, to extract, which will allow us to extract new analytic insights into computing particle production. Specifically, this formalism is going to allow us to identify a certain topological characteristic in it. Okay? So before I delve into the details, let me tell you what particle production is and why do we care. So essentially, if I have a quantum system, the vacuum state contains virtual particle and antiparticle pairs, which are constantly being created and annihilated. So these virtual particles can, if there is an external energy input into these virtual particles, they can go on shell, and this is what essentially leads to particle production. Two famous examples are Schwinger pair production and Hawking radiation, where the energy input, external energy input, comes from strong electric and gravitational fields. In cosmology, something similar happens, where the role of the strong field is played by the time dependence of the background to which the fields are coupled. So suppose I have a field which is coupled to an expanding space-time geometry, then the expansion of the space-time is going to rip apart the virtual particle-antiparticle pairs and put them on shell. So this is essentially what cosmological particle production is. But why do we care? Essentially, the first statement is that it's an inevitable quantum process. Secondly, it has a wide range of pheno implications, one of which is that it is the primary production mechanism in a class of dark matter models called super heavy dark matter models. Okay, with that motivation, it's probably obvious that this is a well-studied problem. What is the new aspect or that I'm going to tell you about? The takeaway of my talk is the following. The long wavelength particle modes produced through coupling to a time-dependent background measures the topology associated with asymptotic expansions. What I mean by this will be clear as into the details, but for now, I want you to think of asymptotic expansions to mean a WKB series expansion. Okay? So there is an associated notion of topology with these expansions, and we'll see that the particle production captures this notion. Great. With that, let me start setting up my problem. Here, particle production is essentially occurring because of breaking of time translation invariance. So let's consider a scalar field, which is coupled to a time-dependent background, 5D. The coupling is such that chi now sees an effective time-dependent mass. Now, if I want to quantize this field over this background, I would write it as a superposition of creation and annihilation operators multiplied by the mode functions chi and chi conjugate. These functions satisfy our solutions to this second order differential equation, the mode equation, and some boundary condition. Corresponding to different boundary conditions, we have different solutions chi's, corresponding set of creation annihilation operators, and an associated notion of vacuum, which is defined as the state annihilated by the annihilation operator A. Now, in time-dependent systems, for the vacua associated with different boundary conditions are in general physically inequivalent. So particle production in this scenario can essentially be understood as a result of a mismatch in vacuum. Okay. To make this more precise, let me start by defining a measure of breaking of time translation invariance, which we call the non-adiabaticity parameter, epsilon. It's defined as the derivative of omega over omega square, where omega is the dispersion relationship of the particle mode. Now, consider a scenario where the epsilon parameter dies down to 0 in the asymptotic future and in the asymptotic past. In these, and in some finite interval in between, it takes non-trivial values. Now, in regions where epsilon tends to 0, time translation invariance is approximately restored, energy is approximately conserved, and here we can have well-defined notions of single particle states. Here, we would associate the WKB functions, the negative WKB function or the positive frequency mode, with associate this function to the notion of a single particle state. So now if I want to quantize this field in the asymptotic future or past, I would do it with respect to mode functions which satisfy the boundary condition that in the future or in the past, they asymptote to the negative WKB function. Then the creation annihilation operators, BB dagger, create single particle states in the future, whereas AA dagger create and annihilate single particle states in the past. Now, in time-dependent scenarios, essentially these sets of creation annihilation operators, AA dagger and BB dagger, are not related by simple proportionality. Instead, they are related by a linear superposition. How do we see that? Chi1 conjugate, Chi2 conjugate are two sets of linearly independent solutions to our second order differential equation, the mode equation. So then these have to be linearly related. The coefficients alpha and beta, which characterize this relation, are called the Bogoliubov coefficients. Given that these mode functions are related by this superposition, the creation annihilation operators AA dagger and BB dagger have to be similarly related by the same coefficients. Okay. Now, this relation is important. It tells us that if I started out in the vacuum state in the past, which is annihilated by A, then as time evolve, I evolve into a state which is not annihilated by B anymore. Okay? So with respect to BB dagger, I'm in an excited state in the future, and the number of particles in this excited state is exactly given by the absolute value square of the Bogoliubov coefficient beta. So our goal is to compute the coefficient, the Bogoliubov coefficient beta k. To do that, we can rephrase the problem in this way. Essentially, what we are doing is tracking the evolution of the WKB functions as we go from the past to the future. So in the past, we started out with a negative WKB function, and our time evolved into a superposition of a negative and a positive WKB function. The coefficient of the positive WKB function, beta k, is what gives us the particle number in that for that value of k. Okay. So if I want to compute these Bogoliubov coefficients, I essentially want to track the evolution of the WKB functions. So then we can rephrase the problem in terms of exactly these functions. So I can rewrite my mode function chi and its derivative in terms of the WKB mode function f minus, f plus, times coefficient functions alpha of eta and beta of eta, which track how these WKB wave functions evolve with time. Now, the Bogoliubov coefficients that we saw in the previous slide would now correspond to the asymptotic limits of these functions. So if I take eta to plus infinity, that would give me the values of the Bogoliubov coefficients that we saw in the previous slide. In terms of these functions, the second order differential equation, the mode equation, can be rewritten as a first-order differential equation, which can be integrated to give a propagator u, which is defined as the path-ordered exponential integral of this matrix M. And this propagator matrix tells you relates the values of alpha and beta between any two instants of time. Great. So then if we want to compute Bogoliubov coefficients, we want to compute the propagator u, take eta 1 and eta 2 to minus infinity and plus infinity to get the Bogoliubov coefficients out. Okay. So now, are these objects easy to compute? Definitely from the exact expression for this, a path-ordered exponential integral of oscillatory functions, it's quite evident that an exact analytic treatment is intractable. Instead, there are standard approximation schemes used to get some analytic estimates, one of which involves the saddle point approximation. So to leading order, the Bogoliubov coefficient, the leading order in the non-adiabaticity parameter epsilon, which is here omega prime by omega square. To leading order in this parameter, the Bogoliubov coefficient can be written as this integral if I started out in the Bunch-Davis vacuum. So Bunch-Davis vacuum corresponds to having started out with the negative WKB function in the asymptotic past. So alpha would correspond, alpha at minus infinity is +1, beta at minus infinity is 0. Okay. With this Bunch-Davis vacuum, the Bogoliubov coefficient can be approximated by this integral. And this integral can, to get an estimate of this integral, we can do saddle point approximation. Here, note that the saddle points correspond to when the derivative of the phase goes to 0, so corresponds to zeros of the dispersion relationship. So this approximation is a good approximation for scenarios where the zeros of the dispersion relationship are well separated. We previously saw that omega squared looked like k squared plus some time-dependent function. So then this essentially implies that this is a good approximation for the large K regime. Okay? So if I wanted to see how the Bogoliubov coefficient exponentially drops after the physical time scales in the system, then this is a good approximation to take. But if I wanted to know the long wavelength or k tending to 0 limit of the Bogoliubov coefficient, then this approximation does not help, because in this limit, the zeros would converge and saddle point approximation is not good anymore. Another approach which leads to similar results as saddle point, it was introduced by Enomoto et al., who computed Bogoliubov coefficients using the idea of Stokes phenomenon. So here we can reproduce the results of the saddle point approximation, but using just simpler analyticity properties of the dispersion relationship omega square. What we want to do now is essentially extend the use of Stokes phenomenon to the k tending to 0 limit and see if we can get new analytic estimates for the Bogoliubov coefficient in the long wavelength limit. Now, I've mentioned that I'm going to use Stokes phenomenon, but I haven't told you what it is. So let's jump right into it. Stokes phenomenon, the statement is the following. Given an exact solution to a complex Schrödinger-like differential equation, its WKB series jumps discretely over certain boundaries in the complex plane called Stokes lines. So up till now, we were looking at the mode function on the real line. Now I've analytically continued the time parameter to complex variable z. So eta has been replaced by z, where z takes complex values. The mode equation also now takes the parameter z. And now the statement is that if I'm looking at solutions to this differential equation valid throughout the complex plane and approximating it in terms of the WKB functions f plus and f minus, then there are certain contours in the complex plane if I cross I would have to correct, or the WKB approximation of my mode function chi is going to discretely jump across these boundaries. Let's take a quick example of array functions. Array functions have a dispersion relationship of have an omega square of z. Let's look at AI of z, a specific solution to the differential equation. A of z satisfies the boundary condition that on the positive real line, it's an exponentially decaying function. If I analytically continue this to the negative real line, then it oscillates as a cosine. Now, this should be odd. This should sound a little odd, because if I plugged in z equal to minus z in the exponential here, then I would get a single oscillating exponential on the negative real line, right? I would not get two oscillating exponentials, which is what a cosine is made of. So in analytically continuing this function to the negative line, at some point I picked up a second exponential corresponding to the other WKB function. The fact that this happens is the statement of Stokes phenomenon. Let me now tell you where these discrete jumps occur and what kind of jumps do we have. So these discrete jumps have been understood to occur across contours in the complex plane, which are called Stokes lines, and are defined by the WKB functions f plus and f minus taking purely real values. So then the imaginary part of their phase is equal to 0. Yeah. Now, depending upon which of the two functions, f plus or f minus, is dominant along these contours, we have two kinds of Stokes lines, plus and minus Stokes lines. Plus Stokes line is the one along which the plus mode exponentially diverges and f minus exponentially decays, whereas the minus Stokes line has the converse. Great. So now, what kind of transformation occurs across these contours? Suppose I started out with a plus Stokes line, and I'm crossing this Stokes line in the counterclockwise direction. Then the f plus mode, which is the dominant mode across that Stokes line, will shift by a constant times the subdominant mode function f minus, whereas the subdominant mode function f minus remains unchanged. So this is how the WKB approximations transform across these contours discretely. If I knew these constants S, which are called the Stokes constants, then I would be able to track the evolution of the WKB functions as I go from negative to positive real line. If I can track their evolutions, then I can compute the Bogoliubov coefficient in terms of these Stokes constants S. Great. So now, are these Stokes constants easy to compute? Well, not exactly, except when there are symmetries in the system. If I'm looking at a very simple dispersion relationship of the form az to the power n, then the mode equation that I began with has a phase rotation symmetry, which is given by this. This, along with the fact that the mode function chi of z is single valued, and hence if I go around in a circle, it has to come back to the same value. These two constraints are sufficiently constraining to fix all the Stokes constants in the scenario as 2 pi cosine pi over n plus 2 as this expression. Okay, so in this scenario, I do know all the Stokes constants in the Stokes lines, so I should be able to compute the Bogoliubov coefficient. But now you may ask, is this dispersion relationship anything physical? Well, in many physical scenarios, the dispersion relationship around non-adiabaticities, around non-adiabaticities can be approximated by this form. And in these scenarios, you can think of the monomial dispersion relationship as the k tending to zero limit or the long wavelength limit. So in these scenarios, we can compute the Bogoliubov coefficient, and it turns out to be the simple expression of cotangent pi over n plus 2. Great. Now, this is a very simple expression, and the simplicity should not be surprising to us because we started out with a very simple dispersion relationship. What is non-trivial about this result, though, is that it allows an interpretation in terms of topological property. So topological properties remain fixed if under continuous deformations of the system. What is the topological property here in the scenario? It's essentially the number of Stokes lines in the system. The number of Stokes lines in the system is completely determined by the order of the polynomial omega square. It does not depend on whether the polynomial looks like a monomial, has symmetrically arranged zeros or randomly arranged zeros. What it depends on is the order of the polynomial n, and is exactly given by n plus 2. Okay? So the number of Stokes lines is also indicates the number of sectors in the complex plane where a certain WKB approximation holds true. And if I cross the Stokes line, I would be discretely jumping to a slightly different approximation. Right? So essentially what this Bogoliubov coefficient or the long wavelength particle number is capturing is counting is the number of Stokes lines in the system. Okay. So this was the primary result of my first paper with this idea. We are now trying to extend the ideas used to compute Stokes constants for the k tending to zero limit to k non-zero. This is work in progress with one of our collaborators, Junji Zhao. And here we see that we can have residual symmetries which relate to Stokes constants. We are now trying to figure out if these symmetries are sufficiently constraining to determine the leading order k corrections of the Bogoliubov coefficient. Finally, I want to quickly show you a model in which these Bogoliubov, in which the topological contribution to the number of particles produced becomes relevant. Okay? So we said that the topological contribution occurs when we have k tending to zero or the long wavelength limit. Now this limit is phase-space suppressed. So if I'm looking at the total number of particles produced, then this usually has negligible contribution. Now instead, if I look at a scenario where the monomial limit or the topological limit happens at a finite value of k, so small k tends to a large k, then in these scenarios, I would have removed the phase suppression, and I can expect a significant contribution from the topological limit to the total particle production. Okay? So the goal of this mathematical model is to present such a scenario where I have a scalar chi, which is coupled to other spectator scalar phi and space-time background, minimally coupled to gravity. The system is such that the spatial curvature is approximately constant for a short interval of time, and during the same interval of time, the coupling to the spectator field phi is such that it gives a monomial dependence. In these scenarios, we were able to compute that the topological contribution is around 10% of the total particle production. Great. So with that, I want to summarize my talk. Essentially, the primary result or takeaway that I wanted to convey today is that the long wavelength particle modes produced through coupling to a time-dependent background measures or counts the number of Stokes lines in the system, which is a topological property. Physical models where the above analysis becomes relevant involve dispersion relationships whose time-dependent part goes through a zero, and the non-adiabatic region can be approximated by a monomial form. Okay? finally, we are now working towards gaining some understanding about the non-zero K corrections to the Bogoliubov coefficient using ideas of symmetry, which were the ones that we used for the long wavelength limit. So that's it. Thank you. If you have any questions for me, I can